Okie dokie, artichoke. Oh my god, it's been so long since I've said that. In this lesson, we are going to be going through accounts on Aztec because they are really, really cool. And I've been so excited to record this video and talk all about accounts just because I just really like them. I think they're real neat. So we're going to be going through what are Aztec accounts, how do they work, and how they're different from anything you've really seen on Ethereum before. And we're actually going to be looking at the code for an account contract. How an account contract actually works is super open-ended for the developer, which has been intentional to keep things least opinionated as possible. But Aztec does have some out-of-the-box accounts for you guys to deploy and also use to learn how accounts work. I will be trying to be as clear as possible about what is an opinionated implementation versus what you actually do have to do for the protocol throughout this video. The other thing I want to note is that you will find the code confusing because it is written in Noir. It's a Noir smart contract. We have yet to look at any of those. So this is going to be your first look at a Noir smart contract. Yay! So I do not expect you to understand how it works. I will just be highlighting the blocks of code and being like, this is kind of what this bit does. This is kind of what this bit does. Do not worry if you get lost. I don't really care at all if you understand the code for the account smart contracts, and I will be clear about what I want you to take away from this video. Nonetheless, I think it is good to have a little look at some code before you even start learning, because the more you see code, the easier it will become. Anyway, I shall stop rambling now because I know I do it a lot. And let's get into Aztec accounts. I am assuming, of course, you are a Solidity developer and you are familiar with account abstraction on Ethereum. If you're not, I will leave linked in the GitHub repo associated with this course a video from Patrick Collins going through ERC 4337 and account abstraction. This video was in the advanced Foundry course on Updraft, but it is also on YouTube. Aztec takes this concept of account abstraction and has built it directly into the protocol. And that has major implications for how things like authentication, authorization, and privacy work. But before we get into Aztec, let's just do a very, very quick recap of account abstraction and how smart accounts work on Ethereum. On Ethereum, you have two types of accounts. I'm going to go through this quickly. You have externally owned accounts, or EOAs, and account contracts, or smart accounts. EOAs are controlled by private keys that are used to sign via ECDSA signatures, and that's it. If you have access to the private key, you have access to the account. There's no custom logic, there's no flexibility. If you want to create a multi-sig, have social recovery, session keys, spending limits, etc., you need to have a smart account. A smart account is where the account is itself a smart contract. The logic is written in code, and ERC 4337 is the standard approach. You deploy a smart contract, the account, which will have a function called validate user op that will define your authentication logic. And instead of submitting transactions directly to the mempool, you have an alt mempool. So like another layer on top of Ethereum. With rather than having validators, you have something called bundlers. And you don't submit transactions, you submit user operations. Bundlers will pick up these user operations from the alt mempool, validate them, and then submit them to a singleton smart contract called the entry point. This all works great, but you're kind of bolting account abstraction on top of an existing protocol that wasn't actually designed for it. And all of the validation logic runs on chain, which means that all the nodes need to re-execute the logic. And this limits how complex it can be and can cause DOS issues. On Aztec, there are no EOAs. Every single account is a smart contract. This isn't an opt-in layer like ERC 4337. It is the protocol. Account abstraction is native on Aztec, and these account contracts can be built literally however you like. It is intentionally open to the developer to implement the logic however you choose. However, as I said, Aztec of course has some opinionated implementations that makes things a little bit easier for the developers to have some out-of-the-box options. Also, you do need to have certain things in order to be compatible with other parts of the stack, like Aztec.js, which is a JavaScript package making it easy to interact with Aztec. So you'd have to kind of implement the front-end side yourself from scratch if you did things differently. Anyway, Aztec having native account abstraction has a few implications. First, there is no entry point singleton contract. Instead, every transaction starts with calling a private function on your account contract. To make it interoperable with the JS side of the stack, this function should be called entry point. And this function is the transaction gateway. It validates the transaction, handles the fee payment in fee juice, and then dispatches the actual function calls to be executed, either via the PXE, so locally for private functions, or via the node for public functions. Secondly, all authentication logic runs on the user's device via the PXE. This is of course because the entry point function is private, therefore it executes locally. Then a zero knowledge proof of the execution is created, and then that proof is sent to the sequencer for verification. The sequencer then just has to verify the proof. They never see the authentication keys or whatever's used. They never have to re-execute the auth logic, and the verification cost is constant regardless of how complex the auth logic is. This means you could have something like a multi-sig, which requires 2 out of 3 signatures, time-locked social recovery, biometric verification, literally anything you can imagine and create a verifier for, and it will cost the same no matter what. Third, this solves the DOS problem. On Ethereum, of course, if validation logic is too expensive, a malicious user could submit invalid user ops and waste bundle of resources. On Aztec, of course, because the PXE generates this fixed size proof, which is then verified by the sequencer's cost is constant and predictable, and invalid proofs are cheap to reject. And the fourth thing is that account addresses are predictable. They are deterministic. A contract's address, so this means any contract on Aztec in fact, is derived from its public keys and contract code before deployment. And this means that you can receive funds at an account contract address before the account contract has even been deployed. This is something we call counterfactual deployment. It's similar to Create 2 on Ethereum, but it's default for every account. Notably, you also don't even have to actually deploy a contract on chain. You could also just initialize it, which is where you kind of call its constructor, which can only be done once, and then the contract exists purely in private. This is a little bit advanced, so I don't expect you to have your head around that right now. We are going to go over this concept again. Now let's take a look at the actual code. So the key takeaways for this lesson, again, don't worry if you didn't understand any of that code, is this. Every account on Aztec is a smart contract. There are no EOAs. Authentication runs client-side in the PXE in private because the entry point function, the function which is called when you execute a transaction, has to be private. Therefore, the sequencer only has to verify a fixed size proof of the execution of this private function, which does all the authentication logic. The third thing is the opinionated accounts on Aztec have 3 main functions. The entry point function, which is your transaction gateway, verify private authwit, which verifies third-party authorization. So you want someone else to be able to execute an action using your account, and is valid impl, which is where you define the custom auth logic. Fourth, everything else is implemented in account actions, so it's all done for you, unless you want to modify anything you choose. Fifth, you can use any auth scheme you like, so this could be ECDSA, or anything else you can write a verifier for in Noir. And finally, complex auth is free for the sequencer. All they need to do is verify the proof. Okay, let's look at an example. I'm looking inside of Noir projects, Noir contracts, account, ECDSA K account contract. And then in this contract, you'll see, I'm going to skip most of the code because it's a little bit confusing as you don't know Aztec ANR yet. Here, this is just the storage struct. And in storage, we are saving the signing public key. So this is the expected public key that we need to verify signatures using. Then we have the constructor to just set this key. Then we have that entry point contract. And in here, this is a little bit confusing, but inside here is where we are actually calling out to is valid impl. This is basically just setting that function as the function for this actions to call inside of actions.entryPoint. Don't worry about it. But yeah, your calling is valid impl inside of here. We then have the verify private authwit function. We're not going to talk about authwits just yet. We're going to talk about that in the later section when we write the token contract from scratch, because authwits are a little bit confusing. And then finally, we have the isValidImpl function, which will take the signature. It'll take the expected public key. I'm going to skip all of that confusing stuff. But then down here, we actually verify the signature. So we take the expected public key, the X part and the Y part. We then take the signature, the hashed message, and check. Like normal, like we do in Solidity, we check whether the signature is valid. And that's it. Thank you for watching. In the next lesson, we are going to be going through Aztec wallets. So do we have MetaMask on Aztec? Spoiler alert, at the moment, no. And wallets actually work a little bit differently because we don't just have one set of keys, we actually have multiple. And the wallet needs to talk to the account, it needs to talk to the Pixie, it needs to talk to the sequencer, and how all of those things intermingle together. So we're also going to be talking through the transaction flow.